Alright, for this problem we're going to be looking at an elevator problem, and this is a little bit more advanced than the most fundamental elevator problems because we're not focusing just on the elevator, but on something that's happening inside of the elevator. And to do that, what we need to do is make sure that we understand what forces are involved. So the first thing I'm going to do is I'm going to redraw this as a very informative box. And this box represents the person. Now, one of the forces acting on this person is, of course, going to be gravity. And gravity is going to act downwards. But then there's another force acting on the person. And it's not the force of the floor directly. The floor is acting on the person, you could say, through the scale by holding the scale up. But it's the scale that's acting directly on the person. And to figure out how much it's acting on the person, we can look in the problem to try to figure that out. So we can see here that the scale is reading 700 newtons. Well, technically what this means, 700 newtons, that's how hard the person is pushing down on the scale. What that does for us, though, is even though the scale is not the subject of our study, we can apply Newton's third law, which says that if the person's applying a force of 700 newtons on the scale is going to apply an equal but opposite force upward on the person. So this is what we would call the normal force. How hard the surface is pushing on the person. Now this normal force here, I'll go ahead and I'll make this the positive direction and this the negative direction. And so this is going to be positive 700 newtons. The other question then is, what is this force of gravity? But that's not so hard to find. One thing that I know for sure is that because it's going to be downward, and I've designated down as the negative direction, it's going to be negative m times g. And with just a little bit of work, we should be able to figure out what this number is. We can plug in numbers. Not going to do it right now. I'll do it a little bit later. So, next step, I think I've identified the relevant forces. One of the things that people get caught up with sometimes on a problem like this is, what about the tension? Of course there's a tension force that's going up on the cable that's causing the whole accelerator to either accelerate upwards or downwards, but it really doesn't matter. We're not focusing on the elevator, we're focusing on the forces acting on the person. And we know that the one is the scale at 700 newtons and the other is the weight of the person, the force of gravity. So I'm going to go ahead and list some givens. And once I examine the problem, I see that we're not interested in position, we're not interested in velocity. So I'm not going to focus in too much on my kinematics types of givens. I'll focus on my force givens instead. So one of those kind of basic force-related givens that we always want to keep track of is the mass. And I can see that that's 60 kilograms in this case. And then acceleration. This is ultimately what we're trying to find. So anyway, the elevator has been descending and now begins to slow down. What acceleration is the person experiencing? So this is what we're looking for. And actually I probably will make a couple of notes over here. The initial velocity is downward. Okay, so I don't know what this acceleration is, but that's what I'm looking for. And then the forces that are in play, I have a force of gravity, which now that I'm over in my givens, I might as well solve for it. So I have force of gravity equals negative m times g. I know my mass is 60. I know g is 9.8. And so we wind up with negative 500, and I probably should have calculated this ahead of time. 88, I believe, is the weight. So here we have the force of gravity, and the last thing to keep track of then is the normal force. And I picked the wrong blue. But the normal force is 700 newtons. So here we go. I have my normal force. How hard is the scale pushing up on the person, which is identical to how hard the person is pushing down on the scale. I have my force of gravity. I'm looking for the acceleration, and I have the mass. So all I need to do now is set up a sum of forces. So I go ahead, sum of forces equals m times a. This I know, this I don't know. But this sum of forces is where we can sometimes get tripped up. I have to identify what forces are acting. And specifically, I'm looking in the y direction, so I might as well just designate that. I'm not too concerned about side-to-side motion. Hopefully the elevator isn't moving side to side too much. And so I have now a force of gravity and a normal force, and they equal m times a. My force of gravity is negative mg. I have my normal force equals m times a. Now the last bit here, I'm looking to solve for a, so I'm going to actually do everything algebraically, which means I need to divide every term, this term here, this term here, and this term here, by m. When I do that, I get the opposite of g plus the force of tension divided by the mass equals the acceleration. I'm just going to do a little line to get it over to here. And now I can plug in numbers. So I have the acceleration equals the opposite of 9.8 plus 700 divided by 60. And for this, I am going to pull out a calculator and do the calculations. So I have negative 9.8 minus 700 over 60, and I get negative 104. That doesn't make sense. I multiplied it. My apologies. So I have negative 9.8 plus 700 over 60, and I get 1.87. That makes a lot more sense than an acceleration in the hundreds. So I have 1.867 meters per second squared. Now, one of the things that you'll notice about this is that it's a positive acceleration. And I know that can sometimes be confusing because the motion of the elevator, I already stated before, the motion of the elevator is initially downward. But bear in mind that it's slowing down. So if you have a negative velocity, a negative initial velocity, and you want to end up with a much smaller final velocity, the only way to achieve that is by having a positive change in velocity and thus a positive acceleration. So this acceleration is exactly what we would expect for something that is slowing down, which the person is doing.